So today we're continuing in 2.6. We are going to graph our rational functions. Now again, just like with our polynomial functions right now, since we're in pre-calculus still, we're just looking for rough sketching, and calculus will help us eventually fill in the fine detail of more details. So some steps that we need to take before we graph a rational function is first we simplify it, meaning we're going to factor the numerator and the denominator and cancel out or remove common factors. We probably want to state the domain because we want to make sure that we're not accidentally graphing a part of the graphing it like it looks like it's passing over a domain restriction. We want to find all the intercepts, both the x and y, if they exist, and find find both if they exist, the horizontal and the vertical asymptotes, and then if we need to plot additional points, we can. Okay, so I thought we would go side by side here and run through a very simple example to start. So the first thing we're supposed to do is simplify. Well, I don't have anything to factor out of this one. It is simplified. So then we will state the domain, which is that x cannot be 2, right? And so then we can find the intercepts. So the intercepts, let's see, if I want to find the x-intercept, I plug in 0 for y, and I multiply both sides by x minus 2, and I end up with 0 is equal to 3. Since this is not a true statement, there's no x-intercept. So this does not hit the x-axis at all. So let's see what happens when we find the y-intercept. So we were finding the x-intercept with this work. To find the y-intercept, then I plug in x is 0. So I have 3 over 0 minus 2, which is negative 3/2. So this hits my y-axis at negative 3/2. So I'm going to put that point on, right? That would be 0, negative 3/2 is a point that I can graph. Oh, I graphed it as if it was positive, so it's really down here. Okay. All right, so found the intercepts. Now we can find our asymptotes. Okay, so vertical asymptotes come from, it's all simplified, from anywhere where the denominator is 0. So this x equals 2, which is our domain restriction, or x can equal 2, becomes x equals 2 is a vertical asymptote. So I'm going to draw that. I use the dotted line there because it's not actually part of my graph, it's just a boundary that'll help me draw my graph better. And now I also want to consider my horizontal asymptotes. So I'm thinking about the degree of the numerator versus the degree of the denominator. Here I have a first degree polynomial. On top I have a 0 degree, right? It's a constant. So that means that the denominator has a higher degree than the numerator, and that's a y equals 0. So I have x equals 1, actually 2 is a vertical asymptote, and I'm going to get y equals 0 is my horizontal asymptote. All right, so really the x-axis is my boundary line. So each one of these, you can kind of, I can plot an additional point in each one of these, but I'm not going to spend a lot of time doing that. But so my graphs will never, ever, ever, ever cross over a vertical asymptote. There are, in fact, graphs that will cross over horizontal asymptotes. If they do, it's usually around the origin, okay? So you can cross over a horizontal asymptote. You know, it's not going to fluctuate a lot, but sometimes you do get a cross. It's usually around the origin most of the time. But you can never, ever cross over a vertical asymptote because that is a domain restriction. That's division by 0, and that just can't happen. All right, so the rest, so this piece up here, okay, so let me just plot a couple of extra points just to make sure that I have the right idea here. So let me choose a number on this side of 2. Okay, so let me put in, we'll do f of 4. So if I plug in f of 4, then I get 3 over 2. I'm putting it in here, so I get 3 over 4 minus 2, which is 3 over 2. So I get 4 and then about 1.5. So I've got a bound here and I've got a bound here, so more than likely my graph looks like this. Okay, so let's pick a point on this side. Okay, so let's say I put in, well, actually I already have a point down here, don't I? I have the y-intercept, and it is bounded from up here and down here, so more than likely it looks like this. Okay, so I have Desmos here, which I thought, so this is the exact. All right, so our graph was pretty close. All right. So, all right, so let's do one that's a little bit more challenging than that. So let's look at this one here. Okay, so the first thing that we want to do, right, from here's our list of things we need to do, is simplify. And so let's factor the numerator and the denominator to look for any common factors. So the top is the difference of two squares. When I have something squared minus another something squared, it factors into two identical, almost identical factors, one plus and one minus. All right, so now the bottom will factor as well. So I get x equals, let's see, so I'm going to have a minus 3 and a plus 1 to get the minus 2 in the bottom, okay, or in the middle, I should say. And so I notice that I have these two common factors. So that means I'm going to work with just this, x plus 3 and x plus 1, as long as I'm not putting in 3. So this is kind of the way we write it. Like, it is the same function, all except for this. And I have the graph of both of these, so we'll see what happens when these two functions, I'll prove it to you that these two functions basically are identical except for right here at this point. Okay. So now that I have my factors simplified, so let's also state the domain here. The domain still comes from the original. Okay, so even though I canceled out this factor that repeats, it still doesn't mean I can plug in x equals 3. So my domain restriction is that x can't be 3 or negative 1. Okay? All right, so let's find intercepts. Okay, so if I find the x-intercept first, then I plug in 0 for y. So I have 0 is equal to, I'm going to use the simplified version. If I use the other version, I should get the same thing. Well, actually, I'll get an extra one that I can't use. So no, you really do need to use the simplified version. Okay, so we're going to work with this, right? This is like our new function, except for when we went back to the domain. So I multiply both sides by x plus 1. This side turns into 0, and I get x plus 3. Leaving me with x equals negative 3 as my x-intercept. So I have negative 3, 0 that I can put on my graph. Okay. All right, and so I should find the y-intercept now. So that means I'm going to plug in 0. And so when I plug in 0, I get out 0 plus 3 over 0 plus 1. And so my y-intercept is positive 3. So then I get 0, 3 here. Right. So now I have those 2 points. So let's look at our asymptotic behavior. So our vertical asymptotes come where the denominator is equal to 0. So I'm going to use this function, which means that x plus 1 equals 0 gives me x equals negative 1 as my vertical asymptote, which is right here. I have matching degrees in my f here, and so my horizontal asymptote will be the ratio of their coefficients in front of x, so that's 1 over 1, so I end up with my horizontal asymptote here at y equals 1. So I have a point up here and boundaries here, so probably my graph looks like this, and then this piece down here looks like this. Okay, so let's see, I think I have this graph here. That's the previous graph, so we're going to take it and its asymptotes off. This time we're going to graph, so this is the graph of this one here, okay? So that I've gone back to the original. Let me put my asymptotes in here. Okay, and then somehow I've changed this. Let me change this to be the actual one. I'm not sure. The slider. Okay. All right, so if I close this now, oops, I lost my vertical asymptote. Where is that? Okay, so now I can see my vertical asymptotes. If you want to graph your vertical asymptotes or your asymptotes on Desmos, then you just hold down that little color button and it gives you a choice of colors and styles. So my dashed lines are my asymptotes, right? And I do see that here at x equals -1, it does match my graph, right? There it is. I mean, my graph isn't perfect, but there's my, oh, it's not giving me, oh, there we go, at 0, 3, right? That matches. And then I have this point here, which is at -3, 0, which also matches mine. And then it looks like my vertical asymptote is in the right place at x equals -1. And my horizontal asymptote is here at x equals, or at y equals 1. Now I wanted to show you, so this is the original. I put in this version, right? This is the unsimplified version of this graph. So look what happens when I go here. Now this is the problem with graphing software, okay? So you have to know things because graphing software is not perfect. So x equals 3 is not part of my domain, right? Because I stated it right here because I had this x minus 3 as a factor. So look what happens to here when I get here. See how, oops, I can't make it stay there, but you can see the undefined pops up when I pass over it, okay? But when I take my finger off of it, it looks completely filled in, right? So that is a hole. Like I can see it when it'll show me just in that one little spot, so it's undefined. So when we go to graph that, oh, I've left that spot off here. That means over here at 3, this spot here should be a hole like this. So I need to mark that on my graph. The way that I can find the y value that goes with it is to plug in the 3 here, right? So if I plug in the 3, I get 6 over 4, which is 3/2. And that is approximately where it is here at 1.5. So, I mean, I do get a point out of this one, right, because I've canceled out that bad part. But it's not part of my original domain, so I mark it like a little open circle. Now, just to show you, I've got the other. So this is the original, and then this is the simplified version of it here. You see, I've got the simplified version. So I'm going to put that on top of it. What you're going to see is you can't tell the difference, right? So my whole graph just turned orange because the orange is sitting directly on top of the purple graph, which was the original one. And so they look identical, right? The only difference is that here, if I can make the numbers pop up again on my actual graph here. Here, when I go to pass over, oops, I've got the purple graph. Hold on, let me take the purple graph off now that we can see that they're the same, and just look at the orange one. So when I go to this one, at 3 is perfectly acceptable, right? Because there's no domain restriction on it. So when I hit 3, right, I just get a number, 1.5, which is 3/2, which we found when we put it into the other one. So a problem, and your graphing calculator is going to show you the same thing, is you're not going to be able to see the hole unless you touch the graph and look for it. But these two graphs look identical except for, right, that the previous graph had that little undefined space. All right, so let's look at our last example here. All right, so we have this time another rational function. So we'll start out by simplifying first. So this will be equal to, I'm just going to factor everything in sight. So this becomes x plus 2, x minus 1. This becomes x minus 3 times x plus 2. And let me state my domain first here. My domain will be, because this is my nice unsimplified one, x cannot equal 3 or -2. So now I'm going to simplify, and I'm going to work with this one to graph it. So I have x minus 1 over x minus 3. Okay, so let's find our asymptotes, or actually, let's find our intercepts first. Okay, so I'm going to find my y-intercept. That means I'm going to plug in 0 for x. So I have basically my y-intercept will be 0 minus 1 over 0 minus 3. So I get positive 1/3. So I have the point 0, 1/3. Okay, my x-intercept means I'm going to plug in 0 for y, and I get x minus 1 over x minus 3. I'm going to multiply x minus 3 by both sides. It's going to cancel over here, and I'm going to get 0. So basically, I'm dealing with x minus 1. That's going to be true all the time. Your zeros come from the numerator. I get x equals 1. So I have this point here. So this is the point 1, 0. All right, so let's look. I have a vertical asymptote at, right, my unsimplified denominator, I get x equals 3. My horizontal asymptote will be y equals 1 because I have degrees matching. Again, ratio of those coefficients is 1 over 1. It's y equals 1, right? These are equations of lines, so let me put these in here. So there's all my boundaries. Okay. Now this piece here, I've got probably enough pieces here that I can graph it. I can kind of see I got this boundary up here. It's got to pass through both of these and sync, right? Because I bump into that vertical asymptote. So that's nice. One other thing that I need to put on is I really should put on my hole. I really probably should have put that in my list of things. So my hole will occur, at -2, which I've already graphed, right? So I'm going to have to put a hole in here. So this is the part, right, that x equals -2 isn't, that's going to give me a hole right there. So let me put it in here and figure out where it is. So if I plug in -2 here, I'm going to get -3 over -5, so at positive 3/5. Oh, that looks about right, right? So I have a hole right there. All right, so let me plot one point on the other side of my vertical asymptote here, just to make sure that I think we're probably up here, but let's just double check. So this was the line x equals 3, so let's choose a number like 5. If I put 5 in here, I'm going to get 4 over 2, which is 2. So that means I have this point right here, and it is up there, so more than likely it does this behavior. Okay, so I do have that also here, so we can look at that. Okay, so that's this graph here, and I have I'll put my vertical asymptotes on, or both my asymptotes, and hopefully this looks right. It looks very similar to mine. So I should see back here at -2, if I click on this graph here, I should find an undefined place. Yep, right there. All right, so we're going to learn how to graph these more precisely later, not that far away, but for right now, so this is kind of, we're learning the basics so that when we get to calculus, if we get the calculus wrong, we at least have an idea of what things should look like. So that'll help us make things more precise.